Welcome back, everyone, to our fourth and last lecture of the day, Krystal.
Okay, so today we get to see the Weiss-Lehmann algorithm in sort of in action, but it is too complicated for me to run on any graph in any dimension bigger than the color refinements. Okay, so what do we do for Weiss-Lehmann? So more formally than last time, let X be a graph. I think in general you can run this Weiss-Lehmann algorithm on a colored graph. So you have labels on colors on the vertices and colors on the edges, and the isomorphisms must preserve the colors. But anyway, we will just do it on an unweighted graph. So just a graph on n vertices. Ooh, LaTeX is awake today. I almost wrote vertices. All right. So so we will color the k tuples, so the elements of v of x to the k. So these are going to be all k tuples of vertices. So then if we let S be some k tuple, so there's v1 up to, so this is in v of x to the k. So this is one of the things that we want to color. So remember in our heuristic definition of the algorithm, at the first step, we color with some isomorphism thing. And then each subsequent step, we will color your group, your tuple, with the colors of its neighbors. So now I better tell you what its neighbors are. So let's maybe 4 have that. The following is going to be one set of neighbors, and then you'll have all possible of these. So S prime of x is just all the ways you can replace one of these vertices with a vertex x. So this is equal to the set, some copy and paste, where I'm allowed to replace v1 by x, and you get the idea, v2 by x, and then there are k choices for where I can stick this x, and I get one of these for each x in v of g. And note that these are tuples, so vertices can repeat. So now with this definition, we're ready to say what happens in the algorithm. So at time I, or the iteration, the ith iteration of the k-dimensional Weiss-Lehmann algorithm, we will color vertex v with L sub I, L sub I like this of v. Okay, so v will be a tuple, and this is how we're going to color them. Okay, so I'm going to tell you what they are. So first, or maybe 0f, so L0, 0th iteration, L0 of v will be the isomorphism class of v in the following way. Okay, so two tuples, if you have x1, they need to be equal as labeled graphs. So it will be basically the vertex, the isomorphism class of the subgraph that is induced by these k vertices. So you have x1 up to xk, and y1 up to y. Okay, v is also a legitimate choice. Okay, so I have these two k tuples. They will have the same isomorphism if the following hold. So 1. So again, these vertices are allowed to repeat in this tuple. So if xi is equal to xj, vi has to equal vj. That's to ensure that the things that are the same in the other one. Note that you are not allowed to reorder xi's and vi's to make this somehow true in a permutation of this. This tuple is really ordered. So then the other thing is that if xi is adjacent to xj, then vi has to be adjacent. So basically, what has to happen is, as a labeled graph, these two have to be isomorphic, and you cannot take a too creative of isomorphism. Like the isomorphism mapping x1 to v1, x2 to v2, this thing has to induce an isomorphism between them, and then they get the same label. So maybe not the same isomorphism class, but they will have the same label if this happens. So at L0, you put whatever label this is, and then at the subsequent L's, you put the colors of its neighbors, and the neighbors are all the possible S prime of X's. Whew. So, and then for I greater than 0, we have L sub I of S. So the sum x1 through x sub k. This is the thing that needs to be colored. Okay, maybe this is a little bit inconvenient. So let's maybe go back to this S notation. Sorry, S denotes this particular tuple, and then I'm going to tell you what the label of S is going to be in the next iteration. So it's going to be some set. The first coordinate is the label in the previous one, in the previous level. So I'm going to have L sub I minus 1 of S. And then as a multiset, what does it, does anyone see the error? Gabriel, assignment. Okay. So, and then followed by the multiset of all the possible labels of the S prime of X's for all values of X. Okay. So it's going to be L sub I minus 1 of S prime of X for all the elements of S prime of X for X in V of X. So maybe this is a little bit imprecise, but you really do put all the labels into a multiset of all the things that are off by 1 in any position. So in other words, a large number of labels every single time, right? Because there are k places where you could stick a new vertex and n choices for each location. So there will be k times n labels inserted into the second multiset. Is it okay? So this is the algorithm. And again, these labels that we're assigning, these L sub I, it will partition the vertices of the graph at every step. At the 0th step, you just partition with respect to the, sorry, not the vertices of the graph, the k tuples. And again, it will terminate at some equitable partition that we're not going to specify. But this will definitely terminate when it gets to singletons. So this will terminate and it will output some partition of these and output some partition of the graph. So there's a lot of research about how fast this will run, how many iterations you need, whether it will be linear in the number of vertices or linear in the number of k tuples, because that would be bad for large k. And yeah, but we're not going to really go into that. We're just going to discuss what this means in the grand picture of things. So Maria asked last day, what does it mean for them to be equal? How do you determine graphs that are not distinguished by this? So we can use Isomorphism algorithm as a heuristic for graph isomorphism. So meaning that if we run it on the k-dimensional thing on graphs x and y, so if we run it on graphs x and y, and then we look at the output, if the partition is not the same, like the shape of the partition is not the same, then the graphs cannot be equal. If the labels are not the same, the graphs cannot be equal, etc. Right? And then if they are equal, same labels, same classes, then we're just going to output that they are not distinguished by the k-dimensional isomorphism. Okay, so if the labels are the same, the set of labels, and the partition is not able to distinguish x and y, then we say that x and y are not distinguished the k-dimensional Weisfehler-Lehmann. So maybe I can try to place this in more context. There are lots of results about how you can say that graphs are really, really similar, and when they would not be distinguishable by some level of the Weisfehler-Lehmann algorithm. There's, but we'll give several examples, maybe today, but definitely tomorrow. So my basic plan is to sort of place this in context in some way by giving one example now. And then today I'm going to define, hopefully, the extensions of the cellular algebra of a graph and K equivalence, which will also give some bound on the Ks that can distinguish some graphs given their equivalence via this algebra. And then basically there will be some number of open problems because it's not very clear what is the optimal algebra to use for this in terms of what captures the equivalence of Weisfeld-Lehmann and other similarities graphs, and also what is easy to prove. Because I think that the algebra we're about to see today, it's somehow easier to see that it's very powerful, but then very difficult to show that graphs have the same one, have weak isomorphisms. Okay, so, oh, sorry, we're about to see two examples. So now we have examples of, why? Oh, okay, bracket, yeah.
Question.
Yes?
So, for your L sub I x, you have L sub I minus 1s, where s is the K before.
Yeah.
This one is L sub I minus 1s prime.
Yeah, so I think it should be this T for each T in S prime of X and for all X. So that whole thing for all X.
You mean
Yeah.
L sub I minus 1 of T, yeah.
Yeah, of T. T is an element now of S prime of X. I was using the set wise notation to be lazy, but you caught me. All right, thanks. So yeah, it should just be all of them. Okay, so examples of connections to Weisfeld-Lehmann, and we will give two. So first is this theorem of Lovash, no accents, right? 1980.
Yeah.
On the A
Yeah.
is like acute?
Yeah.
No, the other one?
No, that's correct.
Okay. So for this we need something. So do we remember what a graph homomorphism is? Morphism between the vertices. It's a mapping between the vertices which preserves edges. So it maps edges to edges. So here we need to let hom of FG denote the number of homomorphisms, a graph F to a graph G. Next week, Dave Robertson will speak, and he will also use this homomorphism count to denote something. Is there a macro? Oh, there's a macro. Okay. And yeah, so this will be connected. What did Lovash show? He showed that if G and H are, so what did he show? He showed that if you count the homomorphisms from, you have, okay, maybe let the graphs be, let G and H be graphs. So you know that Krystal did not do this. So if you have that the number of homomorphisms from F to G and from F to H is equal, all graphs F happens if and only if G is isomorphic to H. There's a proof, there's a short proof in Chris's book with Gordon. And also it would be true if you reverse the roles of F and G here. Okay. And then there was a more recent result. Yeah, so if you have that these homomorphism counts agree for all possible graphs, then the graphs are just isomorphic. In which case, the Weisfeld-Lehmann for any dimension should definitely fail to distinguish them. Okay. So there is a theorem of Dell, Grohe, and Rattan, I can't pronounce these, from 2018, which shows the following. So if the same condition, the homomorphism count is correct, so you have two graphs, G and H, and if the homomorphism counts agree, not for every F, but for all trees F, this is from the earlier paper. Okay, for all trees F, then color refinement. So the first dimensional Weisfeld-Lehmann does not distinguish G and H. Okay, but actually they can do a little bit better, and we're going to leave that up because the class of trees is very nice. And how does it extend? So for all graphs F, so if the homomorphism counts agree for all graphs F of tree width at most K, then the K dimensional Weisfehler-Lehmann.
What is tree width? Is like spanning tree and the longest path?
No. It's a very, very much more complicated thing. So it has to do with you need to somehow place the vertices of your graph into bags such that those bags which have edges between them, if you replace that with an edge, the bags would form a tree. But you can place a vertex in many bags, and the number of bags it lives in, how big the size of the bags are, that contributes to this number here. But anyway, it's a structural thing. It comes up in the proof of the graph minors theorem. It's defined in like paper number 8 out of 23, and lots of yeah, we had to read that one. And lots of things in algorithmic graph theory use tree width as a measurement of how complicated a graph is.
Okay.
They have renormalized this K number of the tree width such that trees now have tree width 1. They used to have tree width 2. And yeah, that was also sad because the things you need them to live in 2 balls.
Yeah.
Okay, but anyway, it's just a structurally measure of how complicated the graph is, basically, if you consider trees to be the least complicated and complete graphs to be the most connected. Yeah, but we can't define it, I'm not able to here. So the K does not distinguish G and H. So basically, the point of the second theorem is that their theorem up here, which is very nice and all the words are understandable, is extendable in exactly the way that in a very nice way as well. Okay, so let me just make sure that was correct. Yeah. Okay, so that's one example. There is a connection with the homomorphism counts, and Dave Robertson and Laura Menchinska, who none of whom are online, they do have a result that says that if these homomorphism counts agree for all planar graphs, that happens if and only if they're quantum isomorphic to each other. So that's a thing for next week's mini course.
Is it true that if they agree for cycles, then the graph equals spectrum? Right?
Yes.
Yeah.
Yes.
Yeah.
Yeah. Homomorphism counts.
So the easiest one to prove.
Yeah,
All this.
yeah. Yeah, of all of these things, yeah, if the homomorphism counts, maybe that's even worth noting. Note that if or maybe I can stick it here. Note that if the homomorphism counts agree for all cycles F, then G and H are cospectral with respect to the adjacency matrix. Okay, and this is just because the characteristic polynomial, its coefficients will be determined by the number of closed walks, and the traces of the powers of A are determined by the number of closed walks. So yeah, homomorphism counts will linear combinations of closed walks of smaller lengths, and then this will happen. Okay, so homomorphism counts. I didn't want section, I wanted subsection. So another example is now we will finally see the symmetric powers, which we will come back to later today with the matrix algebras. Ooh, okay, less optimistic about that. Okay, so recall that I said that symmetric powers were a thing. So, the kth symmetric power, a graph X, is a graph such that the vertices are the k subsets of X and are adjacent when the symmetric difference, right? So you have 2 k subsets, let's say A and B, and it must be, they're adjacent if A contains exactly 1 vertex that is not in B, B contains 1 vertex that is not in A, and these 2 vertices are adjacent. Okay. I think the history of this business is that Rudolph, it was proposed by Terry Rudolph. He wanted to do it for the symmetric square where you have pairs of vertices, but then a bunch of authors, Audinot, Gotzel, and I think Royal, and also Rudolph, they came and they proved that that can't happen for strongly regular graphs. these things will not be distinguished. So for strongly regular graphs, a symmetric square will not distinguish them. And then they propose this kth symmetric power to make it more powerful. And they propose that the spectrum of this thing distinguishes graphs. So it is also, it was proposed by Audinot. Do you know how to spell it?
A-U-D-E-N-A-E-R-T.
E-R-T. Oh, okay, that looks more correct. Okay, thank you. It was proposed by this set of co-authors that the spectrum of the kth symmetric power will distinguish. So there are some refutations, but they didn't actually claim this for all graphs. But let me just give you one example of a theorem about this. So there are two papers, or maybe many papers, but in particular, there's a paper by Alzaga from 2010. I think it's from 2008, but the published version is 2010. No comma. Okay. Which relates it to the Weisfehler-Lehmann. So their result is that if the 2k dimensional Weisfehler-Lehmann does not distinguish G and H, or maybe X and Y, then the kth symmetric of X and Y spectral. So these are actually more complicated statements, but I've simplified them all so that they could be readable in terms of the Weisfehler-Lehmann algorithm and just which dimension distinguishes which things. So hopefully this is a bit of a less rigorous statement of these theorems, but this is what is shown in the paper, and they do it using algebra. And we will also discuss a result that came out in the same year on the archive of Bargy and Ponomarenko, which proves the same result. Yeah, but without the Weisfehler-Lehmann algorithm, but with the algebra that we will try to define later today. Okay, and there's a theorem. And why did we reduce it to this? There is a construction, Führer, F, and Immermann from 1992 that we will hopefully define on Friday, which gives for each k pairs of graphs which are not distinguished by the kth dimensional Weisfehler-Lehmann. Okay, so there will always be graphs who will not be distinguished by the kth symmetric powers. There will always be these pairs. However, it is still open whether or not there are strongly regular graphs who are not distinguished for any k. None of these graphs here are strongly regular. And in the other paper of Bargy and Ponomarenko, we will pronounce his name at a later step. I'm sorry. Ponomarenko. They're also not strongly regular. So there are no strongly regular counterexamples for any k except k equals 2. So however, it is still an open problem to find a pair of strongly regular graphs which are not distinguished. Okay, non-isomorphic strongly regular graphs which are not distinguished by the spectra of their kth symmetric power, where k is at least 3. So that's something to chew on. And also you can start drawing those graphs when you stop paying attention to the lecture, right? So let's see the work at the end. Okay, so let's define the matrix algebra, which maybe will help with this. Extensions. So anyway, that was just how the Weisfehler-Lehmann relates with the other spectral graph variants that have been proposed. But now let's look at the tools for studying it. And this is sort of now we will define some cellular algebras that are extensions of the usual cellular algebra of a graph, i.e. the cellular closure of its adjacency matrix. We'll discuss these extensions, and for two of these to be equivalent, it's not enough for them to be weakly equivalent, but they need to be equivalent in such a way that all of the lower extensions are also equivalent via the same equivalence. So yeah, we're going to have to extend our previous notion of weak isomorphism. But that's not a problem. Let's just dig into it. So let W be a cellular algebra. For us, and for practical uses, we will take this we will consider W to be the cellular algebra, the cellular closure of the adjacency matrix of some graph. We will usually take W to be, why is this key so big? The cellular closure of the adjacency matrix. So cellular closure, again, is a smallest cellular algebra containing the adjacency matrix. Okay, so we will now define the kth extension of W. And this, we're following a paper of Ponomarenko and Evdokimov, and also of Bargy. What is it going to be? Well, it's going to be something that is basically n to the k, where n is the original size of these matrices, the matrices that live in W. Okay, this extension will contain W to the, will contain the Kronecker product. So you want to define something, the bracket, okay, good. So you want to define something which will be of the correct dimension. You want k-fold tensor products of the elements of W. You want the algebra which contains all possible k-fold tensor products of the matrices of your original W. But if that's all that it contained, it wouldn't have any spectral information because you could still diagonalize that with the eigenvectors of the original cellular algebra. So it will contain a little bit more and other stuff. Okay, but it really will only contain one other generator that will come with a lot of extra baggage. So we're going to have to consider one specific matrix, delta, capital delta, sub I. It's going to be a matrix indexed by the elements of v to the k, v of x to the k. X is the ground set of W. Fine, okay. Maybe we can just take W to be the cellular algebra of some graph X. So now it's just the cellular algebra of a graph, and then we're going to take v to the k. So it's matrix indexed by the correct set. So it's the right size to be multiplying with these matrices here, and it's going to be a diagonal matrix. It is a diagonal matrix. The diagonal entry delta I xy is equal to 1 whenever x is a tuple, y is also a k tuple, and they're both equal to the same vertex repeated k times. So it's not the identity matrix. It's a diagonal matrix that has significantly fewer ones on the diagonal. So for example, if you had the vertex u, v, 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 and x and y both equal to that, it's not getting a 1. It's only the same vertex repeated many times. So this is the only extra generator. So now the kth extension, of W is the following. We're not going to, so the main source of this is following Jamie Smith's thesis, and he really insisted on putting hats on these W's, but I can't really type them fast enough, so there will be no hats. So it is just the cellular closure, W to the K, so the Kronecker product as previously defined, and this extra matrix. Okay, so one thing to note that this is much bigger than this first factor here. That when you get to take this diagonal matrix and multiply it with stuff that is in the tensor product of the cellular algebra, you get a lot of new things.
So this is not the same as Gauss-Sarkis extension. This is quite different from Gauss-Sarkis extension. Both ones are out.
I don't know how those are related. I'm sorry.
He takes the k-fold tensor product and then just takes the sub-algebra of things that are stabilized by this symmetric group SK.
I think it will contain much more than this.
It's a symmetrized tensor product. You take the form of the constant group. It looks like it's quite different. Okay.
I think it's going to be quite different. I don't know in what way they're going to be contained. Maybe a littler k will be contained in a bigger k. But I don't know what the relation will be, and I'm not going to show you the other matrices. I'm just going to claim this is bigger than the tensor product by itself. And I'm not going to show you what else lives in here, but I will show you what the cells look like. So we will try to look at what the cells look like. But let's look at what the cells of this cellular algebra.
So presumably
Look like.
you have to be very careful with the ordering here, so the like the ordering of the tuples for the delta I matches like the ordering of the like in the Cronut group.
Well, it doesn't matter because there's just this set of v of x to the k, which indexes all of these matrices. So it will have the same ordering. You just have to order v of x to the k to agree with whatever happened here.
That's literally what I just asked.
Yeah, okay, sorry. Yeah. So this thing you can I would not write it as a block diagonal matrix. I think that would be the bad thing. But instead you can write this as a Kronecker product, but I don't think it'll be very beautiful to write out what this has to be because of the what you said about the ordering. I think the only way to work with them is just this is some abstract operator that maps that is only identity on these things, and this is some abstract operator that you can break down by its components. So yeah, that's why it's a little bit difficult to work with matrices in this thing. So what are the cells? So in general, remember that in a cellular algebra, you have a basis of 0, 1 matrices, but the identity does not have to be one of the elements, unlike an association scheme. But there does have to be a subset of the bases which sum up to the identity. So they will all be diagonal matrices with some number of ones. And the partition into which matrices have which ones on the diagonal, that's going to be the cells of the cellular algebra. So let's look at this. Let's see. A curly A be the 0, 1 basis of W, the original cellular algebra, and let P be an array of basis matrices. This is a little confusing also to me, but basically I want to take T to be some matrices A, IJ between 1 and K. So now we're going to say, so now for a tuple x in v to the k, we will say that this k tuple is type T. There's this array that it's a subset of the 0, 1 bases, but I've indexed them in some weird way. And now a k tuple is going to be type T if it has the following property. Okay, so what is the thing that I need? I need for each of these matrices, Aij, if I look at the entry of xi and xj, these were tuples, this needs to be 1 for all Aij. Yeah.
Is the 0, 1 basis unique?
Yes, for cellular algebra. It was a lemma. Yeah, it's closed under shore product. It's defined to be closed under shore product, so you must have some minimal thing, and you can assume it's 0, 1. So you have some stuff. I can define whether or not a k tuple is type T, and so now I'm going to define delta sub T. This should agree with the delta sub I earlier. Be the matrix, which is the identity, all the k tuples. So then this delta T is going to be in this W hat, W to the power K, whatever K we're working with. So there are a lot of extra things that live there. And if you look at this, each of these will be a diagonal matrix, and they will all be in this extension, the kth extension. So whatever the cells of this extension are, that partition of the k tuples, it has to be a refinement of this partition. So this is the biggest. All the cells of the partition must have the same type. So in particular, the cell partition of W to the K must be refinement of the partition into types. And now you have a lot of types because there are a lot of ways to order the basis elements with this double to make these arrays of basis elements. All right, so I don't know if it was illuminating to look at it, but I think that at least you can see there is going to be a lot of extra matrices that live here. There's even a lot of diagonal matrices that live here, and this is basically what the cell partition has to be. Ooh, okay, we're getting very close. Okay, so now we define these k extensions, And now the next thing that we would like to define is to define equivalence in this relation. And this is easy. So remember, I have now I'm in some situation. Let X and Y be graphs with adjacency matrices A and A prime and cellular closures W prime respectively. So we're going to recall that we will say that X and Y as graphs are going to be equivalent if there is a weak isomorphism, and I need its name. Its name is phi, such that phi takes the adjacency matrix to the other adjacency matrix. Stronger than just being weakly isomorphic. So if this is true, then there's already something that are true. So if there's a weak isomorphism like this, then from the results we had the other day, the adjacency matrices, they definitely have to be cospectral because they just get mapped to the other. And then you can also see that this will map the adjacency matrix of a complement of X and the complement of Y to each other. So this will be, they will be cospectral with cospectral complements. So from this already, we will know that they're cospectral with cospectral complements. And now for K extensions, we say that X and Y are K equivalent. If they are equivalent via phi, again, I need the name of the phi, and there exists a weak isomorphism, E hat, which goes from W to the K, W hat, sorry, W prime to the K. $sign, great. Okay, but not just any weak isomorphism. This phi hat, as suggested. Oh, such an ugly hat. Okay, this thing has to extend the previous phi, such that the restriction of this phi hat to the pure tensor, so to W to the O times K, the kth tensor product of W is phi to the K, and it needs phi to the K, and it needs to, in addition, map our special element, delta sub I, to the correct thing. So it needs to go to the other delta sub I. Put delta sub I of X and delta sub I of Y. Okay, let's just accept that it has to go to that other matrix. So this is the weak isomorphism between these extensions. This is the K equivalence between graphs. So then there are a lot of results that we are going to state on the next day. But basically, what Evdokimov and Ponomarenko show is that if the K-dimensional Weisfehler Lehmann doesn't distinguish X and Y, then X and Y are going to be K over 3 equivalent with this equivalence. The K over 3 extension floored will be equivalent. And then conversely, if they are K equivalent, then the kth dimensional Weisfehler Lehmann will not distinguish them. That's one result. Jamie Smith, in his thesis, he showed that remember that S matrix we got from the discrete time quantum walk. He showed that S matrix is equivalent is basically the same as some matrix that lives in the second extension. So what he gets as a result is that if X and Y are graphs who are 2 equivalent, K is only 2, then those matrices that I defined, they will be cospectral. Right. So that algorithm of M's and all, it will not be able to distinguish even 2 equivalent graphs. So somehow looking at this algebra and things that are K equivalent will be very powerful. But and we will go into more detail on what that means. But then you have this additional problem of this thing is very complicated. It's even difficult for me to write correctly within any given amount of time the other matrices that live in here. You can define some cylindrical relations that look like this T. They are the non-identity versions of what I've written here, and they're always guaranteed to live inside the kth extension. But because it's rather complicated, it's not clear what the thing should be. For example, I think that if you're triply regular, as we had in Akihiro's talk this morning, if X and Y are both triply regular and those triple intersection numbers are all equal, then they should be two equivalent. That result is not known. I also think that if there's Jaeger algebras, J3 are equivalent, they should also be two equivalent, but this is also not known. So these are some open problems that once we define them, we will be able to state. But right, so but I will start.
Any questions for Krystal?
Okay. Did you make some strongly regular graphs?
Okay, so let's thank Krystal again. Thank you, Krystal.